It is going to work very good. So if it just works, no problem. Again, if it brings problems, you can just be able to work without it because it will waste a lot of time. So what are we discussing today?
Reaction mechanisms.
Reaction mechanisms. So like we were done with the types of reactions, if I'm not wrong, we did some. So we were to go to polymerization, isn't it?
Yeah.
Did we look at that?
Yeah, I think so.
What did we say about it?
About polymerization?
Yes.
There's two types of polymerization.
Addition, polymerization.
It's something with water.
Polymerization. So this has to do with what we call the combining of several types of monomers to form a polymer, isn't it?
Yeah.
And of course, you have to actually look at the word polymer, isn't it? And you can actually be able to say that this is a compound that has many monomers. A compound made up of many monomers. Or you can even just be able to say it is a compound that constitutes quite a good number of monomers. So a polymer does not have an exact number of monomers that you can be able to use in this case. And of course, you'll find that several polymers will be able to constitute, or actually will be able to get made of quite a good number of monomers that will be able to become so specific depending on how many have actually been able to get used. And for example, I can be told that there's something called polyethylene, an example of a polymer. Polyethylene can be able to have 4,200 ethene molecules. So the ethene becomes the monomer and the polyethylene becomes the polymer. So you can imagine just compressing 4,200 ethene molecules to form the polyethylene. You see, in this case here, for us to have this type of polymerization occurring as a process industrially, we'll have to employ two very important concepts. Number one, we are going to employ pressure, but at the same time, we're going to employ temperature. Of course, if someone mentions about temperature and pressure, you can be able to attest to this that pressure gets considered most if you have to refer to what we call reactions involving the gaseous compounds. In this case, if I say polyethylene, I'm talking about the ethene. The ethene becomes the monomer, isn't it? So in this case, I expect the monomers to be gaseous what? Compounds, for pressure to get employed as far as speeding up the reaction is concerned. So I can't use something like decane, for that matter, or I can't use undecane. Of course, this is number 10, this is number 11, or I can't actually be able to use what you call dodecane or tridecane. Why? Because these ones are in solid state. You see, from number 1 to 4, as far as alkenes are concerned, they are actually gaseous compounds. From number 5 to 10, they are liquids. From number 11 going forward, they are actually solids. Same applies to what you call alkenes. If I begin from F, then I go to prop, then but. These are what? In gaseous state, isn't it? If I start from pent and go to hex and go to hept, these are solid state. No, they are not in solid state, they are in liquid state. So in liquid state, in gaseous state, and of course, I've said from number 11 going forward to maybe even 100, these are actually in solid state. So I can say, to be very specific, the first 3 alkenes are gaseous compounds. The next 6 are in liquid state, and the rest are in solid state. So the physical state changes from one alkene to the other. And in this case, that tells us that now, for us to make polymers, we are actually going to use, for example, the first 3, which are actually in gaseous state, so that you can employ pressure and temperature for them to get compressed. Why? Because anything that is in gaseous state has particles which are far away from each other. So any pressure that gets applied or gets employed, or any temperature that actually end up rising, will speed up the reaction. Why? Because if this is the first monomer, the second monomer, the third and the fourth, of course their particles are far away from each other. And if the particles are far away from each other, then that means that now it is very easy for us to compress these monomers for us to get the polymer. So a high pressure and a high temperature can get employed in compressing monomers to give the polymer. Now, if we have to mention this, we are supposed to understand that polymerization can either be condensation, isn't it, or addition. Now, what brings out the difference between these two? A clear understanding of this can have to actually employ the following. Number one, you will understand that with condensation polymerization, I can give a practical example. If I want to actually have these ones getting explained, I will employ the following. I will say condensation will involve, number one, picking the monomers. So I will say monomer 1 plus monomer 2. Okay, what am I going to get? A polymer, isn't it? And always we shall have another very important product, and that is actually, for example, a water molecule. We're getting the point. Let me give you a good example. I want to make a protein, isn't it? You know that building blocks of proteins are amino acids. A simple structure of an amino acid involves the following. I will say N, H, then I can say C. So this one can be an alkyne. I can just put an R, isn't it? It can be C, H, like that. Then this can be C, the double bond oxygen and the hydroxide. So amino acid has an amine part, an alkyl part, and a carboxyl part. I'm actually taking this amino acid, then adding onto another amino acid, isn't it? So I'm going to write, for example, I can put here, let me say, for example, I can put here C, then double bond oxygen, and I can put here the OH, then I can say R, then I can say N, then I can say H, then I can say H. So I can do this, you see. So in that case, I'm going to have now this one giving me a water molecule, isn't it? So in that case, if you have to talk about condensation polymerization, it's a type of polymerization that can form a polymer and other water molecules are actually also produced as another product. So this involves forming a polymer and other molecules like water molecules or ammonia. See? But this one only forms one product. And of course, addition means you pick one thing, add on to another one. It gives only one product. For example, if I say ethene plus ethene, maybe plus ethene, then plus ethene, you see. So several of these are going to give me only one product, isn't it? That is polyethylene. So with condensation polymerization, two monomers can undergo condensation, isn't it? And in that process, a polymer is given out and other molecules like water molecules. With addition polymerization, monomers of the same type can actually undergo what we call addition reaction, isn't it? To form a polymer as the only product. Any question here? So that clearly gives us the difference between condensation polymerization and addition polymerization. In this case here, this one can also be able to get used in forming what you call. Let me give you an example of another important polymer that can get formed through what you call addition polymerization. For example, I want to make polyethylene. I will use ethene molecules. I will form polyethylene. That's the first example, isn't it? I can come here and say chloroethylene is the monomer, isn't it? What will be the polymer? Polychloroethylene. So polyethylene can be the first polymer formed through addition polymerization. Polychloroethylene can be the second polymer, isn't it? We have what you call polytetrafluoroethylene. So that means tetrafluoroethylene can be the monomer. Then quite a good number of them can form what we call the polytetrafluoroethene. You see. And these are just examples. You have even what you call polypropene. Now, if you are very keen, you'll realize that the ones we are mentioning are only the first three alkenes. Like we have ethene, we have ethene, we have propene, ethene. You see, we have never actually had a chance of getting what you call polybutene. You see, so they majorly actually focus on the first two, ethene and propene. But there's still a possibility of us making polybutene. You don't use alkanes in making polymers. We use alkenes, and we use the first three alkenes. Why? They are in gaseous state, so that we can employ the aspect of pressure and temperature to speed up the reaction. Very good. So, and of course, this other, you can even mention something like perspex. Perspex is the artificial glass that we make. This is also a polymer. You see, it's also actually a polymer, perspex. So these are examples of polymers formed where only one product gets formed with the absence of any other molecule, like a water molecule. So it becomes addition polymerization. This one gives us a polymer and a water molecule. Like, how do I form starch? I pick two glucose molecules. They'll give me a starch molecule and a water molecule. You see. How do I form nylon? I'll say hexane 1,6-diamine and hexane 1,6-dioic acid. Those two give me what you call nylon 6,6, and the water molecule is also given out. So those are examples of polymers like nylon, starch, proteins that can get formed, isn't it, through what you call condensation polymerization, provided a polymer gets given and also other molecules will also be able to get given, like a water molecule. Very good. So I think that gives us a simple description of that. Unless you have a question. So we've said this is the monomer, isn't it? There are n in number, isn't it? So what happens? They undergo what you call polymerization. Okay, what do we form? So a polymer is a very large molecule compound, isn't it?
It's not polyethylene, it's polyethylene.
Yes.
Is it polyethylene or polyethylene?
We always say ethene, not ethane.
Even though it's an alkane.
Yes. Do you know why? Many ethene molecules undergo polymerization. So if you say ethane, then that means the monomer is ethane. Because if you say polyethane, then you have used ethane. So you say polyethene to mean many ethene molecules. Although the structure that you come up with will be able to not have actually a double what? Double. Because you are going to say open brackets, C, and do this. So that means you won't have any. That just tells you that this is only one, but it gets to actually attach itself to other monomers. So it's a continuous molecule. You see, it's a continuous molecule. So it tends to actually extend these other ends. So you always put here an end to indicate that this is just a monomer that has formed this polymer, where the final polymer that we form has an n number of what? Monomers. So you don't say ethane, you say ethene. Very good. So my question is here, what happens in addition polymerization?
Many monomers of the same category is added.
Yes.
To form polymer.
What about condensation? Do you know a glucose molecule?
Any glucose molecule?
Yeah. Can you combine two to form starch? Like someone can ask you, can you try to explain how two glucose molecules can form a starch molecule with the emission of a water molecule?
It can form water.
Yeah, I want you to come and try. It's not hard. Like you say C6H12O6, C6H12O6. Try to break it so that you can have an OH and a H. C6 H12O6. Like, like you can't show how you can form the water molecule like something of this sort.
See, I showed.
Like, if I come to this one, I can come here and say C6H12, isn't it?
O6.
I can even say H11. Okay? Then I say O5. Then I say OH. This is what I wanted you to show. Then you come here and say plus, I can take this on this other side, I can say OH.
OH or just H?
OH. Like I've picked one hydrogen and one oxygen. Then I can come here and say OH again, and then I will say C6, H11,
O5.
O5. So I'm interested in making the water molecule come out. You see? So I'll have C6H12, this is 11, then O5, isn't it? Then of course it's actually combining this other one. What do you have here? C6, isn't it?
Yeah.
Then H11, then O5. Then I'll say plus what? Plus what? So the OH on this second glucose molecule combines with the H on the first glucose molecule to give us the water molecule. So this part and this part have to combine. Now which type of bond is between these two is called glycosidic bond. Glycosidic bond. It holds two glucose molecules together. You see, to actually end up now forming this type of bond with the water molecule getting given. And that step is actually able to give us what you call condensation polymerization. Good. So at the end of the day, we are trying to show how a water molecule can get formed in this case, isn't it? And what I want to say that in this case, if in case you have to talk about like the NH2, the R, and the COOH, this is the amino acid, isn't it? And again, I can come here and say maybe the O, isn't it? CH. I've just done a reverse of that. Then I say RNH2. Then I just want to have this. Okay, so let me see if it's going to work. So I'm saying you're supposed to say NH2 and RCOOH, and I say OOH, isn't it? And I can first say H, then OOC, isn't it? Then NH2. Good. So that I will actually end up doing this. So I'll have NH2 RCO OOCR NH2, isn't it? So there's a bond between the first O and the other two O's, isn't it? So that bond is called peptide bond. Why do you call it peptide bond? Because there are two amino acids combining to give us what you call the dipeptide structure. So this is called a dipeptide structure because it's made up of two amino acids. So the two amino acids get held together by a peptide bond. I've said in a glucose molecule, we expect to actually have another glucose molecule getting attached onto it by what we call a glycosidic bond. So here we are interested in forming the water molecule, which is what we call the condensation polymerization. So this book has further gone ahead and tried to look at what we call reaction mechanism, isn't it? When someone talks about a reaction mechanism, it's actually trying to actually explain to you that it is actually a two-step representation, isn't it? This is where a reaction gets represented in more than one step using chemical reactions. That is actually to tell you that you can first have something getting introduced in the first equation and something else as well gets introduced in the second equation. Like if someone says, if you can use this as a practical example, someone says N2 plus H2 to give you NH3, isn't it? Then the person says, of course, this is 3, this is 2. Then the person says NH3 plus HCl. What do you get? NH4Cl. So you can say a reaction mechanism has to actually employ that aspect of getting an equation getting represented, isn't it? Or you can say a sequence of 2 or more steps, isn't it? Of a reaction represented. So a sequence of 2 or more steps, isn't it? So a sequence of 2 or more steps represented, isn't it, in form of what you call chemical reactions, or in form of what you call chemical equations, can actually become what you call a reaction mechanism. So 2 or more steps, each one represented by an equation. How many steps are here? 2. So it becomes a reaction mechanism. Why? That is to tell you that it is a sequence of 2, or can even be more than 2 steps, isn't it? Which get represented, isn't it? Yeah. Each with its own chemical reaction. It is possible you can get a question asking, what do you understand by the term reaction mechanism? What do you say?
A reaction which involves 2 steps and each has
its own chemical equation. But you can say a sequence of 2 or more steps, each represented by its own chemical reaction. Now, can you show this by having what you call the electrophilic reaction in alkenes, or the radical substitution in alkanes?
The first one or the second one? The second one, yeah.
Like we are looking at radical reaction mechanisms, isn't it?
Yeah.
And what have we said? A sequence of 2 or more steps, isn't it?
Of 2 or more
steps, isn't it?
Yeah.
Each represented by its own reaction, or each represented by its own chemical equation. This cannot be a very good practical reaction mechanism. Why? Because with a reaction mechanism, it involves a 2 or 3 steps reaction represented by its own chemical reaction. Let me give you a practical example. This is what we call radical substitution in alkanes. For example, the first example of a radical substitution reaction in alkanes, I can say CH4 plus Cl2 reaction mechanism. So I've said reaction mechanism involves, to be very specific, a sequence of 2 or more steps, isn't it, in a reaction, each represented by its own chemical equation. The first example of a reaction mechanism that can get shown in as far as A level is concerned is called radical substitution. And obviously, if someone talks about substitution in organic chemistry, you have to refer to alkanes. Alkanes undergo substitution, while alkenes and alkynes undergo halogenation. So that tells us that now in this case, a substitution reaction cannot be an addition reaction, but a halogenation reaction can be an addition reaction, where if I have C2H4, this is ethene. The ethene can undergo what we call addition reaction as a type of reaction, and halogenation as a process. So what does it give me? C2H4Cl2. Look at that. So this is actually a type of reaction called addition reaction. You see? But the process is called halogenation. You know the difference? So alkenes undergo addition reactions, and the process that have to actually get mentioned here is halogenation. So you get the alkenes that we are mentioning here going to that extent of having halogens getting added onto them. You see, they form one type of what? Product. It becomes an addition reaction. But in this case, because it's a reaction mechanism, alkenes cannot show reaction mechanism because they are what you call addition reaction. You see, you just take an alkene, you add a halogen, it gives you one product. Can you show 2 steps here? You cannot. So alkenes, they can ask in the examination, why do you think alkenes cannot have reaction mechanism? you'll say a reaction mechanism will show a sequence of 2 or more steps in a reaction, represented each with its own what? Chemical reaction. Because here we only have one chemical reaction, we cannot show 2 or 3 steps. It can't be a reaction mechanism. So under the reaction of n hydrocarbon with a halogen, we'll always use alkanes with a halogen. They are what we call a reaction mechanism. They are going to show 2 steps, and even 3 or even 4. What will it be? For example, I'm going to have CH3 Cl plus HCl. Then again CH3 Cl plus Cl2. I'm going to have CH2 Cl2 plus HCl. Look at that. Then you have CH2 Cl2 plus Cl2. What do you get? CH Cl3 then plus HCl. Then you have CH Cl3 plus Cl2. I'll get Cl4 plus HCl. This is a reaction mechanism whereby it will show a sequence of 2 or more steps in a reaction, each represented by its chemical reaction. So it becomes a reaction mechanism. So they can ask you in the examination, give any one example of a reaction mechanism. We'll talk about radical substitution among alkenes. You see, where radicals can substitute a hydrogen atom in an alkane, isn't it? To give us these products. It can be a stepwise reaction, getting to represent more than one step. You see? So it becomes a sequence of 2 or more steps, isn't it? In a reaction, each represented by its own chemical reaction. You see? So this one becomes chloromethane, dichloromethane, trichloromethane, tetrachloromethane. You see? Then you can form even a polymer, polytetrachloromethane as the polymer. So that's the first example, the first mechanism. So a mechanism is a sequence of 2 or more steps, each one represented by an equation, isn't it? And it will show how a reaction does what takes place. Good. So next is electrophilic addition to alkenes. What do you think that one means? The first example of a reaction mechanism is radical substitution in alkenes, isn't it? How does electrophilic attack in alkenes show how reaction mechanisms can occur?
The one used by showing of electrons and arrows.
Yes. You're saying?
It's used by showing electrons and arrows.
Electrons that are?
And arrows.
Electrons and arrows.
So that's
to show how the electrons are lost and gained. How would you do that?
Okay, it depends on the equation.
No, you can just use an example.
Okay, any equation. CH4 plus Cl2.
Is CH4 an alkene? I don't think so.
CH2 plus Cl2.
CH2 plus CH2.
CH2 plus Cl2.
CH2 plus Cl2. What is CH2? You see,
it's methane.
You see, methane is a frustrated guy.
Okay, C2H.
Do you know why?
Why?
We don't have methane, we don't have methane. Like if you go to alkenes, the first alkene is ethene, and then the first alkyne is a thine. So we don't have methane, don't have methane. So it's like electrophilic addition in alkenes. If I say electrophilic addition, electrophilic addition in what? Alkenes. Like the most important thing is, I've told you substitution reaction occurs among alkenes, isn't it? And it can be a 2 or 3 steps reaction, isn't it? But now if you talk about electrophilic addition in alkenes, you have to note that addition reactions occur among alkenes, isn't it? Then we should ask ourselves, in this case, when an alkene undergoes what we call an addition reaction, what should it be reacting with? For example, we mentioned some of the reactions that actually have to encompass writing chemical reactions involving alkenes. And we said one, we can talk about combustion, isn't it? Number two, we can talk about what we call hydrogenation. You can mention halogenation, isn't it? You can mention halogenation. You can mention something else like oxidation. And I told you that oxidation involves using oxidation processes that have to encompass or involve potassium manganate 7 or potassium dichromate 6. I told you can as well use what you call concentrated sulfuric acid as an oxidizing agent, isn't it? So if you look at this, I just examples you can do. I'm in class, sir. I'm in class somewhere. I was to have a lesson today.
Oh, the one that you came the other day at 7?
Yes.
But at what time can you make it today?
Maybe I'll be there by 6. I don't know.
Oh, by 6?
Yes.
So I'll do it like 30 minutes and then I'll do it.
Okay, fine.